I have the YouTube page open and it seems that it's not, now it is starting, okay.
It's delay, Robert. If you
mess
around now, they will just see messing around later.
All right, so then I guess let's start with the Flink 112 Ask Me Anything meetup. Here with me today are Timo. Timo, can you quickly, this is Timo.
Hello.
Timo is a core Flink committer working on SQL. Aljoscha is here with us today. He's working on the Flink APIs, and in this release cycle, he has spent most of his time on unifying the APIs. Arvid is here as well with us. He's also a Flink committer, and he's working on underline checkpointing and Flink runtime improvements. And also we have Stephan with us here. He worked on the new sources in Flink 112 and on many, many other things in Flink. My name is Robert, and I'm going to moderate the session this evening or morning, depending on where you are on this planet right now. And we will first talk about some bigger new features in Flink 112. And while we are discussing these new features, you can ask questions on Slido. And I will try to take them into account during the discussion of the new features. And we already have 15 questions, and some of them are more generic, independent of the 112 release. We are going to try to answer as many as we can of these questions as well, once we've talked about the major new features for Flink 112. And after this interview, Ask Me Anything session, we'll also have some networking event where you can meet and greet with the speakers and other attendees using spatial chat. We'll post a link for this once the session is over, and the link is also on the meetup page. So let's get started. The first topic I'd like to talk about is the batch streaming unification, which has made quite some progress in the Flink 112 release. So maybe Aljoscha, could you give us a summary where we are standing with the batch streaming unification on the API side?
Yeah. So to understand what we're working on, it makes sense to first talk about the situation before Flink 1.12. And here, what we have is we have the data stream API, which is used for stream processing. We have the dataset API, which is used for batch processing. And we have the table API, which is the relational API that can do both. And this has historic reasons, but we think that it makes sense that you should only have one API, a unified API that you can use for both batch and stream processing if you don't want to do table API stuff, but more low-level stuff. So our goal is to essentially deprecate the dataset API and make sure that the data stream API can be used for both unbounded stream processing use cases and for batch processing use cases where you have bounded data, and make that work as well as the dataset API does currently for batch processing use cases. That's roughly the goal, because, I mean, it just makes sense that you don't want to have this additional mental overhead of thinking between these two APIs, which one you choose, or when you do something for dataset API and then suddenly you want to execute the same business logic in the data stream or on a streaming input, then you would have to rewrite it. So these are some of the things that that drove us to do this.
And what specific improvements did we do in the Flink 112 release?
That's a good question. So our plan is to make the data stream API, as I said, the unified API that can do both. And what we did is introduce a new runtime execution mode for the data stream API. So now you can configure that you want to have streaming execution, which is the classical execution behavior of the data stream API, or you can say that you want to have batch execution, where we use some different algorithms. So when you know that your data is bounded, you can do a shuffle, for example, for a keybind differently. You can schedule your operations differently. So in streaming execution, all the operations are running all the time because you're doing incremental processing with low latency. In batch, you can process your data in stages. You can first read the sources, then intermediate operators, and so on. And this affects how you can, how efficient you can be and how you can do fault tolerance and some other things. So it should be, if people change the setting, it should just be more efficient when they execute bounded programs with the data stream API.
And how does the data stream API in batch mode compare to the data set API from a performance point of view?
So we did some initial benchmarks when we started this work. To the program that we did is like a basic word count example where we do basically an aggregation on some data. And there we saw that the performance should be roughly on par with dataset API because we're doing the same thing basically. We have yet to run more. We ran some larger scale experiments to see that we are not completely off the mark when it comes to performance, but we didn't yet do thorough enough tests with the final version to be confident in like writing a blog post, which is something that we plan to do, to explain what the differences are and what the performance is and what some of the caveats could be. Yeah, but we haven't done this yet to give concrete numbers.
Mm-hmm. So there's one question from the audience, and that is, what is the expected level of effort to convert a batch workflow to streaming with bounded sources workflow? So if you have, for example, complex joins in your data set program right now.
Mm-hmm. That's a good question. So the basic building blocks are the same between the data set API and the data stream API. So you have your filter, your flat map, your map. These are the same. Where there are differences is in how you do aggregations and how you do grouped aggregations, for example, a group reduce. So there you would have to put some thinking into how you do that. The one thing that doesn't yet work for the data stream API is if you use iterations in the data set API. That's a somewhat tricky topic, and we didn't tackle that yet. So we have an initial thing for data stream API batch execution that works and it can execute some programs, but if you have niche use cases, they might not work for you. And we list these caveats in the documentation. But hopefully the list of caveats will shrink, or that's expected. And we went for the common cases, or the cases that we thought were common first.
Right. So maybe I can add one thing to this. So the first thing that so this is a bit of a journey, like this whole making the data stream API like partially subsume the data set API, right? The first thing that we were trying to do is getting the programs that your streaming programs to execute really well on like old data and on bounded data, right? So you have a streaming program that you're running on the real time stream, and now you actually want to do, you want to do like reprocessing, reinstatement of an application and so on, and for that you basically need to run the exact same thing you already have as a data stream program on the old data, and you don't want to bother about performance tuning RocksDB for this. You don't want to worry about making sure that your watermarks work well with how your Kafka data was maybe backed up in Parquet files and so on, because that tends to be really tricky if you then need to reproduce this exact same thing. And this is all stuff that you don't need to do anymore if you do batch execution with data stream, right? The basically bringing data stream to the point that that you can just convert data set to data stream, and it offers all these operations. Like Aljoscha said, there's a few caveats still there, like there's no iterations yet. Group reduce, there's not exactly an equivalent of group reduce. Co-groups and joins work actually with Windows and so on. And there's like thoughts in the next releases how to make this a bit more smooth, but this is not the primary thing we're trying to do in this release, like subsume data set programs. It was really more support data stream programs on old data.
Yeah, that's a very good point. Yeah, I missed that when I explained it first.
So another thing that is related to this unification is that we have reworked the underlying framework for the sources and sinks, and also some implementations of the sources and sinks. So maybe let's start with the sources. Maybe Stephan, can you give us some insights into what the overall idea is and what improvements we did in Flink 1.12?
Right. So this is work that started in 1.11 with this new source framework. And I would say actually 1.12 makes it actually work, where 1.11 was kind of like a better version. I think 1.12 is the one that where it actually, where the whole framework actually does come together. The motivation for this was very much also around this unified batch streaming story and just making streaming sources simpler. If you look at what the streaming sources originally were in the data stream API, it's very bare bones, right? It's just let's say a run loop where you can push out elements, which is very generic. You can kind of do everything, but it's also extremely low level, right? So as soon as you do want to implement something, you have to implement a lot of things yourself. And then, there were some common reusable building blocks, but still, it tended to be a lot of effort to implement a source, especially if you wanted an exactly one source which participates in checkpointing and so on. So the idea of this new source API was to make a few things a bit simpler, like and to make it work across batch and streaming. And there's the difference that, for example, for batch sources, you tend to have kind of a division between creating the work that has to be done. For example, if you're reading a set of files, just like collecting the amount of files, splitting them if you want to, and then assigning them to the parties that actually do the work, which is what let's say the old data set API sources, the input formats, what they implemented. The streaming formats had this like very bare bones loop that I described earlier, and we're trying to kind of like get both of those things together. So something that supports both the batch use case and the streaming use case, but with a built-in philosophy of checkpointing. So yeah, that's I think the short explanation, like cover both sides and make also the streaming side a lot easier. And then there's like some more nuances to that. I think once we get, for example, into the topic of incremental checkpoints, there's some stuff in the sources. The whole source API is now a completely asynchronous API, which is important because the whole Flink processing stack is actually an asynchronous stack right now, which is important for for things like reliable checkpoints all the time. You don't want the checkpoint to be blocked by a source thread being at some point where you just cannot intercept it at the moment, and so on. So there's some implementation details also which are important there, but from the user perspective, it's really this unifying batch and streaming and making streaming sources simpler.
Cool, thank you. And which sources in Flink 1.12 are based on this new framework?
So it's mainly the file source that we migrated, which includes the file source in data stream in batch mode, also in bounded mode, in streaming mode, where you continuously monitor set up directories for new files. Which on the if you're using SQL, this includes Hive. So basically, if you connect to Hive and you're reading or Apache or C files and so on, this is going through this new stack. There's a let's say a beta version of a new Kafka source in there, which is a beta version of the new Kafka source. But yeah, so we've used this to validate these different sources, but there's still a backlog of sources needing migration here.
Cool, but the old sources are still working.
They're definitely still working. Yeah.
So Aljoscha, do you want to quickly talk about the new sinks or the new sync?
Maybe let me add one thing, right? The old sources still work perfectly, right? The thing that you can only do with the new sources is you can basically say, I'm seamlessly switching between batch and streaming. So for example, saying I'm using this file source against a directory, gives you a batch program. I'm using the file source against the directory and monitor the directory for changes, gives you a streaming program. Same thing with the Kafka source. You're defining a Kafka source without end offsets, gives you a streaming program. You're defining a Kafka source with end offsets, gives you a batch program. So like this seamless switch with the same source, you just like add a small configuration parameter to the source, or you change a parameter, and then it lets you switch the programs between batch and streaming. This is something that only the new sources can do. That's something the old don't support. So with the old sources, you're still strictly stuck in streaming or in data set.
Pretty cool. So Aljoscha, with the syncs, what's the overall story there and the status in 1.12?
So it's the logical next steps. I mean, once you have a unified API, once you have syncs where you only write them once and then they can be used in batch and streaming, then sources, then the next step is that you have syncs that work for both. The issue with, or not, the current syncs for the data stream API, they work well, but what they do is they rely on some of the implementation details. So the syncs the interface is very simple, so the sync implementations, they directly interact with some of the things that we only have in streaming mode, like checkpointing. And they manually work with checkpoints and they commit their work to the external system on checkpoints. So we don't have that in the batch execution. So we needed to abstract those things away and put them behind some common interface. So that's what we did with the new sync interface, where it's a more modular interface. It makes it easier for people to write those things. And then Flink is responsible for the execution. So for streaming execution behind the scenes, Flink would deal with checkpointing and committing results to the outside world, while in batch execution, it would use different mechanisms for that work in batch execution. So that's the basic idea of it. And what we have right now is a file sync implementation based on this new sync interface. So previously there was the streaming file sync, which is what you can use to write rolling files or put them in buckets based on time or some such. And the new file sync is essentially a drop-in replacement for the streaming file sync that works both in streaming and in batch mode. And it actually can be, in a data stream program, you can actually replace the streaming file sync by the file sync, and it is compatible with the state of the streaming file sync. And it can then just continue from there.
So there's one question that really fits well here. Is it easier to implement two-phase commit in syncs now?
I would say yes. So the interface for the sync is somewhat like a two-phase commit sync thing out of box, basically. What you are responsible for as a sync writer is you as a sync implementer, you provide essentially two interfaces. You provide a writer, that's what you have to write, and you write a committer. And the writer is the thing that writes data to the outside system and prepares a commit, if you will. And then the system, Flink, keeps track of these commits, and the committer is the thing that the sync implementer provides that then commits those things. And Flink behind the scenes takes care that we only commit commitables when we have all the commitables, and that we can retry them and those things that you need for a two-phase commit protocol.
Yeah. So in some sense, this is not very different from, if you go back, I think Hadoop had this like writer committer abstraction for a while. I think Spark has something similar. So this is let's say a Flink version that is kind of adapted to the fact that these committers might run sometimes in checkpointing mode. Sometimes they might run in, like batch committers commit at the end of the task. So they're slightly specialized so they can like switch between these two natures.
Then there's another question that is a bit of a follow-up to the question about converting a batch job to a stream with bounded sources. And that is, if I'm currently using in batch group by or reduce group with group reduce function, how would that work in streaming?
Right now, what you can do with the streaming API is you can use a window operation where you say, I want a global window, and then the window function is equivalent to the group use function, where you get the group of all elements that belong to a certain key. This is, I mean, the dataset API is doing things more efficiently than what we currently do in the window operator for batch execution, because we're doing some things that we don't have to do, but it's essentially, that's how you can express that computation. And we can do more things in the future in the window operator to also execute it roughly the same way as the dataset API would. But the thing is that in the data stream API, you can't have operations that just, like the group reduce operation, that take a group of records without saying what you do with the potentially unbounded nature. I mean, you can't just say, give me all elements for the key, because that is potentially an infinite stream. So you either say, I want these time windows, or you say, I don't care, I want a global window. And if the data never finishes, the global window is never finished. But in batch execution, the global window would eventually close. And then it's equivalent to just getting all the elements for a given key.
But would this use the configured state backend, or is this using a different way?
It's using a different state backend. So, I mean, this goes a bit into the details, but essentially, when you use the data stream API with batch processing, you can use all the same primitives that you use for stream processing. You can use timers, you can use state. It's just that under the hood, we don't use a state backend that uses, say, RocksDB or keeps data on the heap, but we're doing something differently, where we essentially group all the records by a given key and then do a scan, if you will, over all the records of one key, and then move on to the next key, so that we don't have to keep all the data of all the keys in memory at the same time. Because in batch, we know all the data we will have beforehand, and we know when we're finished, whereas in streaming, we don't know when we're finished, so we have to keep all the state all the time. That's the basic difference.
So it's a little bit like mapping a window operator to a MapReduce operation or something like that.
Cool. And there's another question. Can you elaborate on multisync in general and in AWS?
On what exactly? On multisync?
Multisync in general and in AWS. So I have to admit, I don't fully understand the question.
I also don't know what it means.
So does it mean like programs that have multiple syncs, like more than one sync, or?
Which is supported in Flink?
Yeah.
Yeah. All right. Yeah.
Maybe the person can clarify what exactly they're referring to. Then we can pick it up later.
Yeah. So then there's another question regarding the Kafka source. So what's the difference between the new Kafka source and the old Kafka source? And can you also please share more details regarding the use of Kafka source with batch mode?
I think the main difference is that so the new Kafka source follows the new stack, so you can use it both for batch and streaming, right? So it produces an unbounded stream if you configure it only with, let's say, starting offsets, or with a configuration that says, take the earliest offsets or the latest offsets, and it returns like a bounded stream that you can batch process if you also give it end offsets or an end timestamp or something like that. I think this is the biggest difference. There's some other differences in that it supports a few things slightly more elegantly, like partition discovery and so on, compared to the existing source, and it behaves better with underlying checkpoints, just by the nature of implementing the new asynchronous source interface. I'd say these are the most important differences. Other than that, it shouldn't be too surprising for users of the existing source.
Okay, thank you. Then there's another question that also relates to the unified question, but maybe let's move on to the next topic and answer the remaining questions.
We can circle back afterwards also if there's time.
Yeah, exactly, of course. But I would like to touch on some other topics as well, because there's lots of interesting things happening. So maybe to close this batch streaming unification topic, there's also an improvement to the scheduler in Flink that schedules work across the cluster. We're calling this the pipelined region scheduler. So maybe, Stephan, can you give us like a 2-minute summary of what this is all about?
Yeah, so the idea there is the following, right? If you're building a system that tries to like treat batch and streaming and mixtures of batch and streaming as naturally as possible, then this is effectively how Flink is thinking about it underneath the hood. It's taking a job and then looking, okay, what are the different, pipelined data flows that are within that scheduler, right? So let's say you have a streaming job that just, it reads from your source and then it does a map and writes to a sink. And then this is like kind of an embarrassingly parallel one. So if you look at it from the Flink perspective, it's like one straightforward stream. And then you have a lot of them in parallel, right? So from the scheduler perspective, this factors in like a lot of individual regions. If you have a streaming program that does a keybind, connects all of the nodes together, then this kind of factors into a single pipeline region. If you're now using a batch program, and the interesting thing is batch programs in Flink, they can actually use a mix of batch and streaming execution if you wish, right? So for example, the SQL engine can say at certain points, let's say I'm doing a join between a fact and a dimension table. It can actually say I'm using a batch shuffle between the dimension table and the fact table because it's reasonably small, and also maybe I'm broadcasting this. So if I want to recover this, I can kind of fall back to a batch shuffle here, and then on the fact table side, you're using a streaming connection or something like that. So because this is a lot of data and you want to save the IOPS for writing it to disk, then you're kind of doing a mixture between batch and streaming. And this pipeline region scheduler will then, for example, factor this into different units to be scheduled, like the batch part before the dimension side, the streaming part that involves the fact table and the join, and so on. And it uses basically then a dependency graph between these streaming units to basically do batching over streaming regions, if you wish, right? And this is kind of a general way that the scheduler thinks. If you have a streaming program, then very often you have a single streaming region or multiple independent streaming regions, and they're basically executed as a whole. And if you have a batch program, then this typically decomposes into multiple dependent streaming regions that then there's batch execution of these streaming stages one after another. So it's both a way to internally basically unify how the scheduler thinks about these things, and it's actually helped us to clean up a few things on the like especially for the batch processing side. So to make sure that we can actually do better resource distribution. We can make sure there's no resource starvation effects when we schedule later regions that are dependent on earlier regions. Like lot of details that if you were running larger batch jobs you used to get into in like 1.11 and earlier, that were due to the fact that we're kind of using a streaming scheduler to schedule batch workloads. And now it's kind of this mix of a streaming and batch scheduler that is used to schedule workloads, and it actually handles both of these sides like as you would expect them to do. So maybe the effect that you're now seeing as a user is that batch workloads kind of start to behave as you would expect it from batch workloads.
Cool, thank you. So the next big topic I would like to talk about are the improvements to Flink SQL. Timo, do you want to give an overview, or should I ask more specific questions about individual features?
I can give a short overview. Maybe let me quickly share my screen because I have also prepared some slides. Maybe that helps some people because like SQL is easier to understand if you just see a SQL query in front of you. Maybe, yeah, I hope you can see my screen. So we have improved SQL quite a lot because a lot of people are working on the SQL stack. We we improved various dimensions of Flink SQL. So first of all, we worked a lot on the connector side. So if you think about Flink 1.11, like we were supporting Kafka, you could configure a JSON format for Kafka. We were supporting event time and watermarks on top of a Kafka connector. What we changed what we also supported in the last version, we also started like initial support of also changelog sources. So for example, we supported Debezium JSON coming into Kafka. In this release, for example, we further improved the handling of connectors. For example, now it is possible to get additional metadata out of SQL connectors. In this case, for Kafka, for example, you can finally configure the key and the value format. You can decide what fields are included in the key format, what fields are included in the value format. You can configure or you can read specific meta information like a Kafka timestamp, the Kafka offset, topic information, partition information, and so on. And based on that, we are now also able, or we introduced a completely new Kafka connector for upserting, upsert Kafka support. So that means instead of treating Kafka as an insert-only log, now we can also interpret like thumbstones in the Kafka log as deletions and so on. So and you can also configure a primary key. So the updates are internally materialized based on the primary key. This is a very big improvement. Then we can go further. Like in this release, you can really see that we are also trying or aiming to do like SQL first. So before you had to configure things in the API and could express some things in SQL. Now you can also, for example, declare temporal tables in SQL or versioned tables in SQL. So by defining a primary key and an event time column, this creates you like a temporal or versioned table. And what that basically means is you have the possibility to either just read from this versioned table, and like internally the updates are applied. So for example, when there is an update on some row, this update will be materialized and you will see it in the output stream. But it also allows you to perform temporal joins, which means that you can basically, for example, if we have a table of orders, that you can query or join two tables based on event time. So here you can just say, like, for this changelog table, for system time as of time of the other table, this gives you basically a view of the table at this given time, and the join will be performed as if both of these tables were joined at the given historic time. So these are the most important changes in SQL. Apart from that, we did a lot of like stability improvements. Also the UDFs are mostly done now. The time system rework is mostly done. So I think users will see that the API is about to like stabilize, not evolving too quickly. Yeah, that's a basic overview.
Thanks a lot. So there's one question from the audience, and that is if there is anything new regarding CDC, so change data capture, in this release.
Yes, definitely. Like in this, like the upsert Kafka is a perfect example for change data capturing. So you can use the Kafka. For the first time, we basically support a real upserting source, and with the upsert Kafka as a sink, also a perfect upserting sink. So you can have, like, when you're using Kafka with Kafka compacted topics, you can really have like a CDC story from beginning to end. And we support Debezium already, so you can also connect your databases or your database logs easier with SQL.
So maybe it would be helpful if you could describe a little bit broader the scenario where you would use CTC and the Kafka upsert connector. So could you maybe describe a little bit broader the systems involved and the typical use cases and so on?
Yeah. So first of all, I would say, like, with Flink SQL, you are very flexible when it comes to systems in general. So we are not bound to Kafka. You can also use different systems. You can connect to databases. The problem with databases is, like, syncing into databases is easier than reading from databases. Databases, like, if you just want to perform a batch job, that's easy. You just perform a table scan over the database. But if you want to continuously consume changes from the database, then you need some way of connecting to the database. And in this case, we support that through Debezium. So basically, the setup would look like you're connecting the database to Kafka Connect in Debezium. From there, you're storing the log of the database, the transaction log in Kafka, and from there you can read the CTC log into Flink. And once it is in Flink, you can decide what you do. Do you want to, like, you can perform some queries, and then you can write out to your favorite system. It can be Elasticsearch, can be again Kafka. You're very flexible basically to choose the target system. And in the future, of course, you can also write, or I think this is also supported already, you can also write to a file system if you want to. I'm not sure how well this works for streaming mode, but it should also work soon, I guess.
Okay.
I think it actually works already, right? You can. So I think a nice use case is this like combining this outbox pattern and materialized views, right? So let's say you have your initial source of truth is some database, be that, you know, Postgres, Oracle, or so, where you're doing the initial changes, and then you're using change data capture to capture them. I think you can actually use the Debezium embedded engine to directly grab it from there if you're comfortable with this, to, you know, hook Flink against the transaction log directly. I think most people will probably put Kafka in between just to, you know, like decouple these things a bit. And then you're consuming this change log to compute different views, can consume different change logs, right? You can have the Postgres database, let's say, for users here, for let's say for orders here, for inventory there, and then like join all these streams to compute derived views and so on, and put them in, be that Elasticsearch, again, Postgres, HBase, or something like that, or just publish the change stream again, like you said. Right? So I think this combination of like database plus capturing the change and then deriving a view from there, this is a really, I think, a very powerful paradigm. Another thing I think that started working with 1.11 and that got some enhancements in 1.12 is, for example, like streaming, ingesting this into Hive then for further analytics. So you can use the Hive streaming sync to continuously ingest these capture changes or these derived views, for example, into a data lake, to like incrementally commit this, register this at the meta store, and make it available for querying with other systems also, as it, you know, in near real time as the data is captured, as the, you know, like the derived watermarks or the timestamp advances and closes partitions, these get published and registered basically continuously. So I think this is also I think a use case that we've seen users adopt, basically, you know, if you're as your first like entryway into stream processing, using this to basically build something like a continuous ETL from either Kafka or from a Kafka outbox of another, like using Kafka as the outbox of another database, and from there doing streaming ETL into Hive, or real-time ETL into Hive, and so on. These are things also really nice use case that works really well with the changes in 1.11 and 1.12.
Yeah. And to note, there is also, it's not just real time. Many people don't know that actually Table API is, or SQL API is a unified API already. So like when people are thinking about migrating their jobs from dataset API to data stream API, maybe it is also worth considering maybe porting parts of it to table API, because there you have already like built-in joins, efficient group bys and aggregations and so on. Like it's really worth also to look into table API, because there the API is already unified for batch and streaming. Just to mention that.
Yeah, that's a great point.
Maybe to make this really clear, I think Timo has a very good point in the sense of a lot of batch jobs in dataset should actually first try to see if there is a good match in the table API in batch execution, and only if that doesn't work, consider the data stream API.
Yeah, or like reach out to us, because like we are also very interested what is actually missing in table API to subsume data set API, like which operations do you need, which are blocking you from migrating to table API. That would be very interesting information for us.
Right, because the data stream API might feel a little more similar to the dataset API if you're used to using Java classes and Scala classes and worrying about the serialization. But ideally, you actually don't have to do this, right? This is the lower level APIs that all these systems started with, versus the higher level APIs, which are centered around like tables, data frames, and so on. Whenever you can actually migrate to those, it's definitely worth trying, because they take a lot of effort from you. It's much easier to make them work in a performant way, because writing like really performant operators and really performant serialization is something that that still has gotchas just by by how Java works and the JVM works and so on. You just have to be aware of a lot of things in order to make it work really fast. And in the table API, all these things are kind of taken care of for you by the code generation phase and so on.
Yeah, so you have like you work on binary data and so on. And the nice thing is like you have this entire ecosystem, catalog support, static type system, schema support, structured data support, like, and yeah, a lot of available source and things that are perfectly integrated with the optimizer. That is a lot of stuff that the data stream API cannot give you, also not in the near future.
So there's one follow-up question that probably fits to this topic. Does the file sync compact small files in Flink 1.12, or is the small file problem still there?
It does for Hive, I think, in particular. Like the SQL file sync, I would have to double check. The SQL file sync with Hive does it. I have to double check if the SQL file sync does it in general, or only if used in conjunction with Hive. So it's something that where the work has started, but it has to yet be pulled through all layers of the stack. So the Hive sync is the first one where it was implemented. I can say that much. Yeah.
Okay, thank you. The next question is maybe a good opener for another topic. Are there any improvements on save points and checkpoints in the new release? Arvid.
So this sounds like a question for me. The big feature that we introduced in 1.11 was unaligned checkpoint. And for 1.12, we did lots of improvement under the hood. So similar to the new source interface, you could say that in 1.11 it was kind of a beta feature, and now we consider it measure enough to be used in production. The one thing that we optimized is the latency that is added through additional shuffles. So, if you have back pressure, this is the main use case for using unaligned checkpoint. Then you have certain operations competing for the main task, for the task thread. And it used to be in 1.11 that if you write data out and no buffer is available, the thread is blocked. And in this at this point, you cannot process anything related to checkpoints, even if you use unaligned checkpoints. You have to wait until one more buffer is written, which means pretty much all the time that on the downstream side, one buffer got processed completely. So With 1.11, with 1.12, we actually changed it that you always have one buffer available, so you can always directly process checkpoints and checkpoint-related information. It means that all shuffles do not add any latency, any end-to-end latency for underlying checkpoints, which is pretty huge for longer pipelines, especially if you use lots of joins, window operations. Even if you use async IO after a source, you have a shuffle. So that's pretty good. It means that it's mostly decoupled from actual data flow. The other remaining or missing feature in 1.11 that you actually had to use is the new source interface. Stephan mentioned it a couple of times already, that only the new source interface is implemented in an asynchronous way, that we can always access the task thread when it comes to checkpointing. That we can always interrupt polling data from the sources so that we do checkpointing. And all the old sources are usually blocking. If no buffer is available, if you have back pressure, that means that you always have some initial offset when checkpointing is started at all on the source level. And then even if you use the new improvements in 1.12, you still have this initial latency when it comes to processing checkpoints in end-to-end. So this was one of the big improvements that we have on checkpointing. Also, recovery on underlying checkpoint is much improved. It requires almost no shuffles when reading the data from the external checkpoint storage.
Is underlying checkpoint enabled by default in 1.12?
No, so unfortunately, we didn't finish two big features that we consider essential for making underlying checkpoint the new default. The first idea is, so currently you can only have underlying checkpoint for all shuffles, for all tasks, or you have still the old way, the align checkpoints, the default way. What we actually want to have is some kind of a timeout mechanism where Flink tries to do alignment first, and only after trying for, let's say, 10 seconds, 1 minute per task, it would switch in a transparent way to underlying checkpoint. The main idea why we want to do this is because if you have some task, for example, in the middle, or only some partitions that are heavily back pressured, you would, by using the timeout mechanism, reduce the number of records or in-flight data that you need to actually persist on the checkpoint storage tremendously. So currently you have to pretty much persist everything that is somewhere in the network stack. And in the future, we only want to persist things that are actually on the very slow path caused by back pressure. So this is a big improvement. And this also means if you enable it by default and you don't have any back pressure, then there is actually no underlying checkpoint happening effectively. And this is what we want to have. If a program is well behaved, if it doesn't have any back pressure, then checkpointing is working in the terms of propagating the barrier downstream good enough. So we don't need underlying checkpoint or the mechanisms that we introduced with underlying checkpoint. And only if we have temporary spikes, if we have consistent back pressure, only then underlying checkpoint would really persist additional data to the checkpoint storage. And only then there's actually a difference between how it's done now. So this is the one big feature that we want to have in it before making it default. And the second feature is actually allowing rescaling. So in the documentation, rescaling from checkpoints is actually, I think, not officially stated as supported, but we think this is an important feature that we had already with the align checkpoints, with the old checkpoints. You can always rescale your job from a checkpoint, which is important if you have a sudden spike. You usually don't have the luxury to take in another save point to rescale. You usually have to work with what's already there. And if you then want to scale up to catch up, then you just want to use the checkpoint. And coincidentally, this is the same scenario where underlying checkpoint is actually most useful. If you have a second spike, you want to have an underlying checkpoint, you get your checkpoint, and then you can rescale, you can catch up. and eventually through the timeout mechanism, your checkpoint become aligned again, the old way again. So these two features we really want to see. Unfortunately, I didn't make it for 1.12, but we are very confident that they will make it for the next release then, because they are quite finished already.
Cool. Thanks a lot for this update.
Stephan, do you want to add something on this topic?
I think you had the most important parts, right? Maybe the thing to spell out explicitly is that the amount of data that is stored in a checkpoint is a bit higher for unaligned checkpoints because some in-flight data is included. So to keep it as cheap as possible, yes, exactly. This like adaptive way of kicking in is something we really wanted to have. Like only if you're actually under back pressure to do an unaligned checkpoint. If you're not under back pressure, then an aligned checkpoint is actually perfectly fine, is what you want to do. So systems should keep doing that. Yeah, the second part that where I can connect maybe with the comment of the sources is this. I think it's a bit interesting just from an architecture perspective. It's not something you see very much as a user, but I think it's like from a system design perspective, it's like an interesting tidbit. So when we started developing Flink, it had very much the nature of like a batch system or a database where you had just operators trying to push data through pipelines, and these pipelines would they would span multiple machines or through the network stack, and like back pressure was just eagerly propagated, and when something would block, it would just block very naturally through back pressure, and that's perfectly fine for batch processing. For streaming, we then found that this is kind of a bit limiting, specifically because of this notion that like if checkpoints only ever flow together with the records, then they can be very unpredictable. And this is what we see with many users, right? If you run a system with like a parallelism of a few thousand under very heavy back pressure, like your checkpoint can take over an hour sometimes. Like there are these cases. And this is where we try to basically make the whole thing like a very asynchronous system where nothing is ever blocking, and where you can basically like capture the state between these asynchronously connected parts at any point in time. So the whole runtime was like rewritten in a mailbox model. The input to the mailbox is asynchronous. That's the new sources. The output of the mailbox into the network stack is now also asynchronous. So this whole operator will only ever do work. It will only ever process a record if it is sure that like everything around it is in a reasonable position. Like there's actually data available in the source, there's actually capacity available in the network stack. Only then would it say, okay, I'm picking something from the source, processing it, putting it to the network stack. Otherwise, it will always stay available for other types of operations, like drawing a snapshot and so on. This is kind of a big change that went on for, I think, 3 releases underneath the hood, maybe 4 releases or so. And I think with this, like with the conclusion of 1.12, this should actually be done now. And I think an interesting case is one of these users where we saw the checkpoints were taking, I think, nearly 2 hours for like a very, very big job with very, very big state and extremely heavy back pressure. And then unaligned checkpoints by itself brought it, I don't have the exact numbers, but I think the rough order was maybe down to something like 35-40 minutes. So maybe to like got it down by a factor of 3-4, but still like surprisingly long. Like why would unaligned checkpoints, why would it take so long? We don't actually need the barriers to travel with the stream anymore. And the answer for that was exactly in this like in what I think Arvid mentioned with the output buffer availability. I'm not sure if this was like if this was clear. It was this notion that the operator could actually never find the time slot or the time to take this checkpoint, because it was too much always like waiting to still put the last remaining bits of data somewhere before it would actually have the liberty to take a checkpoint. For a single record, that doesn't take long, but I think if you compound that through a very long pipeline with like a very high parallelism, this can actually be a pretty big deal. And this is where like rewriting this to a completely asynchronous model actually brought this down to like a matter of like low minutes or so. So it's all these things that come together, or that need to come together in the end to make it happen. So Yeah, kind of a change from a system that like eagerly pushes and blocks to something that really has a lot of asynchronous stages with very like fine control of how the handover works.
Cool. So we have only 5 minutes left. Maybe we can do a few extra minutes to answer the remaining Q&A questions. So the first one is, when can we expect to have auto-scaling, preferably with some kind of Kubernetes integration? So I can maybe quickly take this. In Flink 1.13, we are planning to add what we call a reactive mode that allows you to deploy Flink on Kubernetes. And if you're giving Flink more task managers, or if you're taking away task managers, then Flink will be able to adopt or to adjust to this new resource availability. So it will scale up in case more task managers are there, and scale down if task managers are going away. So this is the first step to auto-scaling that we will provide in Flink 1.13.
So it's one ingredient to auto-scaling, right? For a proper auto-scaling setup, you then need some component that monitors the metrics and decides to add or remove task managers. So on Kubernetes, you could, for example, try to use the autoscalers that make this decision based on like CPU utilization or memory utilization of the nodes. So like these things together can give you then an auto-scaling story.
Yes, by the way, also since the last release, there is a new metric, backmeasure metric, which you can also use to actually see if your task or a particular task is backmeasured. This is what is used by the platform, the Worker platform, to autoscale on Kafka.
Right.
Yeah. Then there's a specific sounding question. It's regarding Flink 18736. And that is the Jira ticket about the source chaining with n-ary stream operator in Flink. And the question is now chaining of multiple different sources, HDFS Kafka, possible in Flink 1.12?
Okay.
I can take this, or do you want to take this, Arvid?
You can just take it.
Okay. So I think the short answer is yes. The more nuanced answer is yes, very easily in SQL, and it's a little bit of manual work still in data stream. So there's so the SQL optimizer is actually making use of this to kind of fuse as many joins together as possible. So no longer have a cascade of two-way joins, but like fuse this together in one n-ary join. And the inputs to the n-ary joins can be HDFS, Kafka network, like pretty arbitrarily, both in batch and streaming networks. You can do something similar in the data stream API. There's an n-ary operator transformation. The way you assemble this right now is a little bit clumsy. That's why we're not advertising this. If you're very eager and you kind of grab for this, you'll find some test cases that show how to do this, and you can probably adopt this pattern. But yeah, it's a little verbose, let's say, to do this. There's a bit of an API shortcut that makes this easy missing. So yes, on the SQL side. And I would say no for most people on the data stream side, unless you really want to, dig deep.
If you wanna really do it, then it's best to just come to the mailing list and we help you.
Yeah.
Cool, thank you. The next question is, when will the streaming file sync support Azure storage?
The issue is that we don't have a file committer for Azure currently.
All right, so the streaming file sync that I'm curious, like, can't you reuse the same techniques that it basically uses for HDFS? Is there significant difference? I'd have to look into the details. If there's some fundamental difference, or if it's just like it doesn't recognize it, that's why it doesn't do it. Maybe it's a really easy thing to change. And yeah.
Maybe it's background for other people. The streaming file sync works with Hadoop file systems, so it should theoretically work with everything that supports that interface, but some file systems like S3 only say they support Hadoop or Hadoop file systems, but they don't. They have some quirks like eventual consistency, or reads don't get everything that is written potentially. So in Flink, we have some abstractions for the file systems that are specific to S3 so that we can work around those limitations. And maybe we need the same thing for sure. Maybe Azure, maybe that's what the issue is hinting at. But yeah.
Right. Would have to clarify. As long as Azure actually supports, I think, constant time renames and truncations, then it should be very well possible to support it. Then maybe it's just not recognized, or like just the APIs aren't connected. Then there's no fundamental issue. If Azure doesn't support like constant time renames, like S3 doesn't, then it's actually a harder issue.
Yeah, cool. Yeah, we can follow up on that using Jira. So another interesting question is, we use large local states. What are the options to have faster job restarts? Our job needs 1 hour to start processing records when you restart from a save point.
Mm-hmm. Who wants to take this? Should I take it? Okay. So there's I think there's a few levels to that question. There's like a bit what can you do immediately and what can you do like conceptually in the future. Like what can you do immediately? Like immediately you can try and use all these like all the options that that Flink added over time, like local recovery makes sure that anything that's like, let's say, a soft failure where or where you're recovering a task as part of a broader failover of another task that it's connected to, that these become very cheap. They don't have to go, for example, to external storage. They can basically just like reopen the local RocksDB or something like that. If you can use, for example, RocksDB incremental checkpoints, they're not only faster to take, they're also faster on restore because they don't rebuild the database. They basically just copy the database image back. If you really have a local state that takes an hour to copy back from, let's say, S3, HDFS, or wherever you're storing your checkpoints to, where the failed task itself, or let's say, okay, in case of a save point, I assume you're pretty much restoring all tasks. So that's where local recovery is maybe not relevant for you. If you're restoring all these tasks, then yeah, there's nothing in the current versions that is going to help you there. There's a few things we're looking into for the next version. So there's kind of been a longer standing issue to say let's look at things like taking save points also in the state backend's native format. So basically having save points where we don't basically just write a sequence of key value pairs, but where the save point actually contains the RocksDB native image, which is a lot faster to restore because you don't have to rebuild the SS tables. You basically just restore them. That is one thing. The other thing is just being able to actually start executing before loading all the data. There's some ideas floating around. I think over the course of the next year, there's going to be some effort that we start there, but there's nothing like concretely available at this point in time. Yeah, it is definitely, and like restoring large save points is definitely something that we do have on our list as an issue that we want to improve, but we don't have a ready solution there at the moment.
I would like to add, if it wasn't clear already by Stephan, I would really consider using external checkpoints as an alternative if it's for recovery of time travel, because they are in the native format and much faster to restore.
Right, that's a very good point. Yeah. So just to spell that out clearly, like the cost of restoring a save point is often twofold, right? It's copying the data to the local disk and then, let's say, rebuilding RocksDB or something like that. And exactly, if you have a save point, if you just, let's say, cancel and you leave the save point, and then restore from that cancel and leave a checkpoint, and then you use this checkpoint for restoring, then at least you save the second part, like rebuilding RocksDB. Then you only have to copy the data. That can already help.
Great. The next question is, when will Verica support Flink 112? So I guess this is about Verica platform, and Verica platform 2.4, which is planned for January, February, will support Flink 112. The next question is, ordered by votes, by the way. Are there any plans for the machine learning library?
Mm-hmm.
So maybe Stephan, a short answer.
The short answer is there's some community effort, but I don't think there's like a concrete timeline. There are associated projects in Flink, like ecosystem projects like A-Link. There's something that's called Flink AI Extended. This cryptic name actually behind that is an integration with TensorFlow and PyTorch. You can find this on the Flink community packages side. These they're ecosystem projects. They're not part of Flink. Adding this to Flink, maybe, it's a big community. Maybe somebody does that, but I don't think it's on the roadmap of anyone in this call at the moment.
Maybe I could add that it would be interesting also to hear on which kind of support of machine learning you are most interested in. So we are currently also debating if we should just support external to like TensorFlow or PyTorch probably, or if we should really build native algorithms on top of Flink. So that would be really interesting to hear on the mailing list, hopefully, that we can discuss and go into detail what's really needed so that we don't have any effort going into the wrong direction.
All right, so I think we are a few minutes over time already. So maybe we'll all switch to spatial chat now, where the audience can just reach out to the speakers here if they have further questions. So I would like to thank each of you for talking about some new Flink 112 features and also answering questions in the Q&A. So thank you very much, and see you in spatial chat. We'll post a link on YouTube so that you find your way to spatial chat. Thanks. Bye-bye.
Thank you, Robert, for moderating. Are we off now, or what's happening?
I think we need to leave now.
Yeah, I'm leaving and I'm going to spatial chat.
See ya.